I'd like to continue our discussion of counting techniques. Sometimes we want to arrange objects in different order and count those different orderings. And I want to just illustrate that with a simple example. Suppose today we're arranging a promotional photo shoot for 3 celebrities. We've got Luke, Han, and Yoda. And I want to know in how many ways can we line them up together for a photo. Obviously, the order that I have pictured them in the beginning is one possibility. I could put Luke first, then Han, and then Yoda. That's not the only way I could choose to do it. If I want to try to get every possible arrangement, I want to do it in some organized fashion. So let's first agree to keep Luke in place as long as possible. So in order to keep Luke in that first position, I need to switch Han and Yoda. It gives me a different arrangement in how I could line them up for the photo. But as long as Luke stays in this first position, there's nothing else I can do to get a different arrangement. So in order to get a different arrangement, I have to move Luke. So let's push Luke over to the middle. If we do that, then I can put Han on the left and Yoda on the right to get a third different arrangement. But if I switch Han and Yoda, leaving Luke in the middle, I'll have yet a different arrangement. And as you can see now, as long as I'm keeping Luke in the middle, there's nothing else I can do to get a different arrangement. So the next thing would be to push Luke to the right. If I do that, I can put Han first and Yoda second to give me a fifth arrangement. Or, leaving Luke where he is, I can switch Han and Yoda and put Han first, Yoda second. Again, keeping Luke on the right. And that's really it. I've moved Luke in every possible position, and once Luke was in that position, I've gotten every possible ordering I can get that's different. So when all's said and done, there are a total of 6 different ways that we can line up Luke, Han, and Yoda for that promotional photo. We could have done this with a tree diagram, and I want you to have an arsenal of tools that you can use for different problems, and different people like to think about it in this different ways. If I did it with a tree diagram, I would get the same 6 results. Each ordering of a set of unique objects is called a permutation of those objects. So if I'm thinking of Luke, Han, and Yoda as the 3 objects, then there are 6 permutations of those 3 people or objects, each one specifying a different order for, say, a photo shoot. Fortunately, we don't have to do this by brute force, by drawing a tree diagram or doing it the way I did earlier. There is an easier way to do this, but it involves something called a factorial. And here's the definition. N with an exclamation point after it, it's read n factorial, is equal to n times n minus 1 times n minus 2, and as you can see, the pattern continues multiplying until you get down to 1. That's called a factorial. Now, I want to return to this problem, so remember this spot, but because the solution to the problem we were looking at originally involves factorials, I want to jump off to the side and talk a little bit about factorials, and then we'll come back to this exact same spot. So let's move and just talk about factorials for a minute. I gave you the definition a minute ago. N factorial is n times n minus 1 times n minus 2, and you keep multiplying until you get to 1. For example, suppose I gave you 4 factorial and asked you to calculate it. You'd simply take 4 times 3 times 2 times 1, and you'd end up with 24. 4 times 3 is 12, 12 times 2 is 24, and 24 times 1 is 24. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. If you calculate that, you'll end up with 720. Now 1 factorial you're counting down, you get to 1, but when you write 1 down, you're done. So 1 factorial is 1. Those are factorials. There is one special case, though. According to the definition above, it works for n equal 1, 2, anything bigger than 2, any positive integer bigger than 2. But we can also define a factorial when n is equal to 0, although we can't use that definition above. And it turns out, and we're not going to go into why, but it turns out that 0 factorial is equal to 1. It doesn't follow this formula above. It doesn't fit into this formula here, but it is the definition of 0 factorial. So just remember that 0 factorial is 1, and for n equal 1 or higher, use the formula. Also might mention that factorials get large quickly, so it's going to be good to know how to use your Casio FX260 to do these factorials. There is a factorial button on that calculator. And if you look at it, I'll show you where it is. It's actually the shift above the 3. So I've blown up the keyboard over here on the left, and the factorial key, the factorial symbol, is above the 3, and you get that by using the shift button first. So if you want to get the factorial button, you have to do shift 3. So just as an example, if I ask you to calculate 8 factorial, first thing you do is put in 8. Then you want to get to the factorial, so you have to do shift 3. And that will give you the answer as if you had typed in 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 and hit equal. And you can verify that yourself. In fact, you should be doing that to make sure you get 40,320. So 8 factorial is 40,320. Now, I told you we're going to go back. We talked a little bit about factorials. I'm going to go back to the problem that I wanted to use factorials on. So we're going to jump straight back to where we were. This is where we left off, and we took our tangent to talk about factorials. So now that I know what factorials are, I want to apply that knowledge to this problem. It turns out that the number of permutations, like this example with Han and Yoda and Luke, which gives the number of permutations of n distinct objects, turns out that count just turns out to be n factorial. So had I known that earlier, I could have just said, well, Luke, Han, Yoda, that's 3. So I'm using n equal 3, and I calculate 3 factorial, and 3 factorial is 3 times 2 times 1, and I've got the 6. And notice that that 6 is the exact same answer we got when we did it the hard way by brute force methods. So this is a big improvement in being able to solve these problems without having to work so hard. These are permutations of distinct objects. Now this is a very important result, so I want to make sure that you've got it. You simply calculate n factorial. I can't emphasize how important this result's going to be. Now let's look at a variation of this problem. What if I added a 4th person? Suppose I added Leia to this group. Now I could go back and do it the brute force way, but I think you might imagine it might take a while. The more people, the more possibilities you have. But since we know that n factorial counts the number of different arrangements, then all we have to do is change the 3 to 4 and calculate 4 factorial instead of 3 factorial. And of course 4 factorial is 4 times 3 times 2 times 1, which is 24. Much easier than trying to do a brute force method. So there are 24 different arrangements possible if I add a 4th person to that promotional video. Knowing the factorial formula is good enough when the number of objects you're arranging is the same as the number of objects you have to choose from. In other words, if you have 4 people and you want to arrange all 4 of them, or if you have 3 people and you want to arrange all 3 of them. But that's not always the case. Last time we took 3 and we took 4 people and lined all of them up for a photo. But what if we were doing something different? Suppose we had those 4 people, but the promotional photo was being taken on, say, a bicycle built for 2. How would that change things? So this time we're still choosing from 4 people, but we don't want to select them all 4 at a time. We only pick them in pairs because a bicycle built for 2 only holds 2. So if I want this bicycle built for 2 to be part of my promotional photo, I'm going to seat them 2 at a time on that bicycle. So that changes things. This time I'm choosing 2 of the 4, and of course sitting on the front is different than sitting on the back. What does that do? Well, let's just list it all out. Let's do every possible arrangement. I'm still doing 4 people, but I'm only picking them 2 at a time now. Think about how that differs from what we did earlier. So suppose I just start off with Luke on the front and Leia on the back seat. That's one possibility. Let's keep Leia on the back seat and put everyone else on. So I'll move and I'll leave Leia on the back, but I'm going to add Han to the front instead of Luke. That's a second possibility. There's one more way that I can leave Leia in place, and that is to put Yoda on the front. And that's a third possibility. Now that we've exhausted every possibility with Leia on the back seat, let's now move and take Luke on the back seat. So I've done every possible way of keeping Leia on the back seat. Now I'm moving to the next person in line. I put Luke on the back seat with Leia on the front, Luke on the back seat with Han on the front, Luke on the back seat with Yoda on the front. That's every possibility with Luke on the back. So I've taken Leia on the back seat, every possible way it can be done. I've taken Luke on the back seat, every possible way it can be done. So now I'm going to move and put Han on the back seat. So if I pair Han with Leia, that's a different arrangement. Han with Luke, it's a different arrangement. Han with Yoda, that's a different arrangement. So now I've exhausted 3 of the 4 possibilities being on the back seat. So now I'll put Yoda on the back seat. Last way to do it. Pair Yoda with Leia, that's a 10th possibility. Pair Yoda with Luke, that's an 11th possibility. And pair Yoda with Han, that's a 12th possibility. And now I'll put everybody on the back seat, and I've paired them in every possible way. So there are 12 of them. There are 12 permutations of 4 objects taken 2 at a time. Keep in mind, this distinction of how many objects you're taking at a time is really very important. Whether you're taking them all at a time, it just becomes a regular permutation, or whether you're just taking some subset of them at a time and arranging. So when you take everybody, say the 4 at a time, take all 4 of them, or if you've got 3 and take all 3 at a time, that's just a permutation. But when you take a subset of the total number of objects, then you've gotten into this situation. And I would describe this by saying there are 12 permutations of 4 objects taken 2 at a time. When I say taken 2 at a time, that emphasizes the fact that I'm not putting everybody in the photo at the same time. Early on, we learned that if we want to find the number of permutations of all the objects, we just calculate in factorial. I'm going to say that over and over again because that's the important concept here. So if I wanted to range all 4 for the photo lineup, it would be 4 factorials 24. We did that calculation. We know that there's a formula for it. The question now is there also a formula for computing the number of permutations when you're not picking them all at the same time? Like this example on the bicycle built for 2, when you're choosing from 4 people, but you're only taking them in pairs. And the answer is yes, there is. There is a formula for that as well. A permutation is defined to be an ordering of distinct objects, and again, you often picture them as being in a straight line. It's just easy to think about them that way. If we select R distinct objects from that set of n objects, which is what we were doing with the bicycle built for 2 problem, and arrange them in some order, we call that a permutation of n objects taken R at a time. And we use this notation, capital P with n comma r in parentheses after it, and that's read a permutation of n objects taken r at a time. So the distinction when you're taking them all is just called a permutation, and you calculate by doing n factorial. If you're taking a subset, but you're still arranging in order, that's called a permutation of n objects taken r at a time. And it has its own formula. Well, I've alluded to it, but what is that formula? Here it is. The formula is a little more complicated than just doing a factorial. You take the factorial of how many you're choosing from. So in the problem with Leia, Luke, Han, and Yoda, that would have been 4. So you take 4 factorial, goes in the numerator, and then you take the difference between the number of objects and how many you're choosing at a time. So in our case with the bicycle built for 2, it'd be 4 minus 2, because you're choosing from 4 people, you're taking them 2 at a time, and do the factorial of that. So a permutation of n objects taken r at a time is a fraction. In the numerator there's n factorial. In the denominator you take the difference between n and r and make a factorial out of that. And when you simplify that result, you get the answer. So if I go back and apply that to the bicycle built for 2 problem, let's show that this formula actually gives you the same answer, which was 12 that we got by doing it by brute force. So all I've got to do is remember I was choosing from 4 people and I was taking them 2 at a time. So n is 4 and r is 2. And if I plug 4n for n and 2n for r, I end up with a fraction with 4 factorial on the top and 2 factorial on the bottom. Now remember, 4 factorial is simply 4 times 3 times 2 times 1, and 2 factorial is 2 times 1. And of course that gives us 24 over 2, which is 12. So it's exactly the same answer. So these brute force methods will work for small values of n and r, but when you get to large numbers, you really have to use the permutation formula for practical reasons, of course. Again, we're in luck. Not only is there a factorial key on our Casio, there's also a permutation key. And if you look on your calculator, it lies right above the number 1. So again, you're going to have to hit the shift key to get to it. But otherwise, very straightforward process. If I wanted to use that calculator to calculate the permutation of 4 objects taken 2 at a time, I would take the number 4, then I would get to the permutation key, which is shift 1. The combination of shift followed by 1 gets you to the permutation key. Then you put in r, which in this case is 2, and to make it actually do the calculation, you press equal. And if you do that, and you should be following along on your calculator with this, you will get 12, which is exactly the same answer we got before. There is another interesting fact that if you think about it, has got to be true for what we've done to work. But if you take this formula above and let r be equal to n, in other words, this r just becomes n, then in the denominator you get n minus n, which is 0, but 0 factorial is 1. So it would just become a 1 in the denominator. So the interesting thing is that when you take them all at a time, in other words, if you've got 4 people and you're taking all 4 at a time, it just turns into a factorial. Well, as I said, we knew that had to be true because that's the thing we did first. When we did the problem with Leia, Luke, Han, and Yoda and just lining them all up, we were doing it as a factorial. But you could also say it's 4 people taking 4 at a time, which means r is equal to 4 and n is equal to 4. It has to come out to be a factorial. So, interesting fact, but if you followed along with the discussion, it had to be the case. Let's change the problem slightly yet again. This time, instead of taking the 4 celebs and lining them up for any type of photo, whether on or off the bicycle built for 2, let's suppose now we're just going to pick 2 of them to get their star on the Hollywood Walk of Fame. Well, this time, That's totally different because it doesn't matter what order you choose them. It just means they both get a star on the Hollywood Walk of Fame. So in this problem, you're still choosing 2 from 4, but the difference is order no longer matters. You don't care what order you choose them in. Well, how does that differ? If I choose Han and then Yoda, or Yoda and then Han, it doesn't really matter because they just both get stars. So I don't want to count those as 2 different choices as I would have earlier. Problems of this sort where order doesn't matter are called combinations. So permutations, order is always foremost in your mind. The order matters. In fact, the order is what's important. When you're doing problems like this with combinations, you're only interested in how many different choices you can make, not worrying about order. So be thinking about ordered versus don't care about order. But let's go back to the problem. It's actually easy to answer this question given that we've already gotten the 12 possibilities when order does matter. So if I just look back and pop those 12 possibilities back up, all I have to do is get rid of the ones where they're the same if you don't worry about order. For example, 1 and 4 are really the same if I don't care what order they're chosen in. Choosing Leia and then Luke is the same as choosing Luke and then Leia. They just both get a star. It doesn't matter. So I can cross out one of those. As I go down that list, I can keep doing that. 2 and 7 are the same. Choosing Leia then Luke is the same as choosing Luke and then Leia. So I can mark one of those out. And just continue doing this. 3 is the same as 10, so I can mark one out. 5 and 8 are the same. Both have Luke and Han. I get rid of one of those. 6 and 11. Get rid of one of those. 9 and 12 are the same. They both involve Han and Yoda, so I can get rid of one of those. So when all's said and done, I'm only left with 6. So out of the 12, I've got 6 left. Is there a formula for that? Yes, there is. Because it was 6 versus 12, you might think it's just half, but that is not true. It just happened to work out that way in this problem. The formula, for better or for worse, is more complicated. There is one. A combination is a subset of a set of distinct objects where order is not important. If we select R distinct objects from a set of N objects without regard to order, we call this a combination of N objects taken R at a time. And the notation for that, it's not necessarily just one, but the one that you see the most often, the one that we will use, is a capital C with N comma R in parentheses. And it's read a combination of N objects taken R at the time. The formula is a little more complicated. And what I would point out is, if you just look at part of it, it looks just like the formula for the permutation. If you just take the part that I've boxed off, that is the formula for a permutation, the capital P. But when you put that extra R factorial in the denominator, the permutation becomes a combination. So again, I'm not going to derive the formula, but that is the formula for a combination. It's the formula for permutation with an extra factor in the denominator, that factor being R factorial. Let's go back and use this Hollywood Walk of Fame example to see if we can get the same answer we did before. Remember, we got 6. And for this problem, there are 4 people. There's still Leia, Luke, Han, and Yoda, and we're choosing them 2 at a time to get stars on the Hollywood Walk of Fame. So order doesn't matter. That means it's a combination. So I simply put 4 in for N here and here, and R equal 2 here and here. And when I do that, I'll end up with, realizing that 4 minus 2 is 2, I end up with 4 factorial in the numerator and 2 factorial times 2 factorial in the denominator. And if I write out what each of those things simplify to, I end up with 24 over 4, which is 6. Same answer as before. So I'm building up a toolbox of formulas I can use for different problems. If I'm just grabbing a set of things and putting all of them in order, and I'm checking for how many different ways you can do that, that's just a permutation. If I'm taking that same set, but I'm just choosing a subset of those objects, that's a permutation. And if I'm choosing a subset of objects but I don't care about order, then that's a combination. So you need to think your way through that and start being able to recognize a problem and what tool you'll use to solve it. And lucky us, we have a combination button or key on your calculator that will do that as well. It's above the number 2. It works just like the permutation button, except you do shift 2 to get to it instead of shift 1. So if you wanted to calculate a combination of 4 objects taken 2 at a time, you would do exactly as you did for a permutation, except that the shift 1 would change to a shift 2. So you'd put in the 4, then you'd do shift 2, then you'd put in the 2, and then equal. And what you come out with is 6. So follow along, try that yourself, and make sure you get 6. Let's summarize. Also keep in mind that you might need more than one tool for a single problem. And if you don't have the tools in your toolbox, or you can't extract them as you need them, you're going to have problems. So let's do a summary of the techniques with the idea in mind that we're going to come across some problems where not only do you have to choose which one tool to use, sometimes you'll be using more than one. So this is very important. Going all the way back, we had the fundamental counting principle, what I call the FCP. It says a task composed of a series of subtasks in which the first subtask can be performed in A ways, the second in B ways, the third in C ways, and so on, can be done in A times B times C, continuing the multiplication that many ways. We already knew that from an earlier discussion of accounting techniques. Now we've added the permutation formula. That's for n distinct objects taken n at a time, and it's just n factorial. And we've added the permutations of n objects taken r at a time. That's when order matters, but you're only taking a subset of the objects. And then finally, we have the combination. So when we're taking a subset of objects, we're taking r objects from a group of n objects. But this time order doesn't matter. It's like the Hollywood Star of Fame example, where it doesn't matter what order you're chosen in. Let's take this example and try to use our toolbox of counting techniques to solve this problem. It says the computing committee at a college has 5 administrators, 7 faculty, and 5 students. So that's a total of 17 people on that committee. A 4-person subcommittee is to be formed from that 17-member committee. The subcommittee chair and vice chair must be administrators, but the rest of the subcommittee can be composed of any of the faculty or the students. And the question is, how many ways can this subcommittee be formed? You've got to take this apart, because this is a little more complicated than the simple case of this is just a permutation of all the objects. This is a permutation of some subset of them, or this is a combination. This has more to it than that, so you have to take it apart. The first thing I would say is, in part of the choice, order matters, because you're going to select a chair and vice chair, and they have to be administrators, and the first one you choose, say, is going to be the chair, and the second one will be a vice chair, so it matters which is which. There's a difference between being chair of a committee and vice chair of a committee. So for part of the problem, order matters. That's when you're choosing the chair and vice chair. But it says the rest of the committee is just whoever from the faculty or students. So if you choose one faculty, one student, or 2 students, or 2 faculty, or some combination thereof, it doesn't really matter what order you get them in, they just pop onto the subcommittee. So this problem has 2 aspects. Part of your selection procedure is going to be choosing an ordered arrangement. Part's going to be an unordered arrangement. And the number of ways you can do both goes back to the fundamental counting principle. You just take the product of the ways of doing each individual. So my idea is just to break this whole thing into 2 subtasks. The task of choosing the 4-member subcommittee is broken down into the task of getting the officers and then getting the other 2 separate subtasks. And then I'll apply the fundamental counting principle to get the final result. In other words, the number of ways to choose the 2 officers by the fundamental counting principle times the number of ways to choose the other 2 is going to be the final answer. So I've broken this problem into 2 tasks. Task 1 will be choosing the two officers, and task 2 be choosing the other two, and then I just make the product of those two subtask solutions to get the final result that I'm looking for. So that's my strategy. Divide and conquer. As I said earlier, because order matters for the officers, this is going to be a permutation. So it will be the permutation of, remember, the officers have to be administrators. The chair and the vice chair must be administrators. So they have to come from the 5. And you're choosing 2, one for chair, one for vice chair. So that's a permutation of 5 things taken 2 at a time. Now I move to task 2. For choosing the other 2, I don't care about order. I just grab 2 of the people that are either faculty administrators and throw them on the committee. It doesn't matter which one's chosen first. So that is a combination. Order doesn't matter. And remember, it said that the other 2 can be anybody from the faculty and students. Well, that's a total of 12. So if you take the faculty and students and add together, you get 12, but you're still choosing 2 of them. So that's a combination of 12 objects taken 2 at a time. And that's task or subtask 2. So what I want to do now is calculate each of those, simplify them, and then take the product. So let's do the calculation for the permutation first. That's a permutation of 5 things taken 2 at a time. I will leave it to you to do that in your calculator. Remember, you're going to be doing shift 1 to get to the permutation. So it'll be 5, shift 1, 2 equals. And you'll come up with 20. Then do the same thing with the combination. But remember, the combination is shift 2. So you'd be 12, shift 2, 2 equals, and you'll come up with 66. And then you take 20 times 66, and you'll get 1,320. So using the fundamental counting principle and the formula for permutations and the formula for combinations all in the same problem, you find out that that subcommittee can be formed in 1,320 different ways.